This set of notes is intended to introduce the idea of an antiderivative and corresponds with section 5.2 of the textbook. So recall from chapter 4 that a differential equation is an equation that contains the derivative of a function. And so we're going to consider differential equations of this form. And so let's kind of look at the left-hand side and the right-hand side of this equation and see what this tells us. So looking here at the left-hand side of the equation, notice what this is telling us is this is telling us the rate of change in y, and that's because we're taking the derivative of y with respect to x. And remember, when we very first introduced the idea of derivatives, we saw what the derivative is actually telling us is the slope of that tangent line. And we saw that when there was a greater rate of change, that would be the higher the slope. And if the function wasn't changing as much, we would have a lower slope for the tangent line. And so this is why the derivative of the function y with respect to x, that's going to tell us the rate of change in y. And notice we can see by the way that this is written that that rate of change in y is a function of x. And again, we're taking the derivative of y with respect to x, and then that is equal to, again, some function of x. And so in other words, when we look at that rate of change of y, it is a function of x and it only depends on x. So in other words, the rate at which the dependent variable change only depends on the independent variable. And so in this section, we're going to address two important questions. So if we're given the differential equation, how can we find a solution? So in other words, before we looked at the function and we found the derivative, now the question is, well, what if you're given the derivative? How do you find the original function? And if you find a function that corresponds to that derivative, is the solution unique? In other words, is there only one function that corresponds to that derivative that you're given? So in other words, we want to find functions y which satisfy y prime, and that prime isn't very clear here, but that is y prime is equal to f of x. So in other words, the same thing that we had up here, just different notation. And we'll see that if we can find a function, then it ends up there's a whole family of functions rather with this property. And if we want to pick out one of those functions, we need to specify an initial condition. That is, we need to be given a single point on the graph of the function, and if y of x satisfies both the differential equation and the initial condition, we say it's the solution of an initial value problem. And so we are going to look at examples where we find not only families of functions, but we'll also look at initial problems. At this point, probably reading this sounds a little nebulous, but once we start looking at some concrete examples, I think this is going to make some more sense. And if we have a function that we think solves a differential equation, we can verify the function indeed satisfies the differential equation by differentiating that. And we're going to do that in each of these examples. So for the examples that we look at here, we're going to start out with that derivative. We're going to try to find out which function would give us that derivative, and then we'll actually take the derivative of that function to see if we got the first thing that we had. And so what this method suggests is that in order to find solutions, we actually need to reverse the process of differentiation. And this leads us to what is called an antiderivative. And so a function f, and notice here we have a capital F, is an antiderivative of f where we have a lowercase. And this notation, it looks a little funny because it's like, oh man, we're just using f and capital F's and lowercase f's. But it's good at this point to kind of get used to this style of notation, because when you start to use these ideas in your probability course, you'll see that we'll also use the capital and lowercase letters, and they have very specific meanings when we get to that context. So for now, we're going to work with this notation, but do kind of keep in the back of your mind that this style notation is not going to go away. We are going to use that in your future courses. And so again here, the function capital F is what we call the antiderivative of the function little f on the interval I if the derivative of f of x is equal to the original function. And so the idea here, what we're going to be doing is we're going to have f, and we're going to see if we can find the antiderivative. And again, we're going to look at lots of examples, and I think through the examples, this is going to help. So let's start out with a couple examples here. So we want to find the antiderivative of the function e to the x. And so in order to find the antiderivative, we need to find a function whose derivative is e to the x. Right, so that's why it's called an antiderivative here. You're really given the derivative, and then you're asking yourself what function would have this as the derivative. And so again, in contrast to everything that you've done up to this point, you've been given the function and you found the derivative. Here, we're saying that this f of x, this is the derivative. And then our question is, that should say what is f of x, where f of x is the function that would give us that derivative. And so, the notation here just gets a little bit confusing because previously up to this point, we had used little f of x to define a function, and then we say, well, what's the derivative? Here, we're using little f of x to say this is the derivative. What function is going to give us that derivative? But remember that the derivatives we've seen were functions themselves, so we can use this notation still. It's just how we're phrasing the question about these equations that changes. All right, so back to our question here. So we want to find, if we're going to find the antiderivative, we need to find a function whose derivative is e to the x. Well, we know that the derivative of e to the x is just e to the x, so we could guess f of x is equal to e to the x. And so notice, if I take the derivative of capital F of x, I would get still e to the x. And so that matches what I have here. So that is a valid antiderivative. But what about the function e to the x plus 6? Notice, if I take the derivative with respect to x of this capital F of x, I would still get e to the x. And that's because the derivative of 6 with respect to x is just 0. So this is also a valid antiderivative. And so what we end up doing when we define antiderivatives is we use the following. And so here I've got e to the x plus c, where c is a constant. And so notice, no matter what value I replace into c, if I take the derivative of capital F of x, I am always going to end up with e to the x, or in other words, lowercase f. And so what we have here is a whole family of functions that if I take the derivative of any member of this family of functions, I'm going to end up with that, again, lowercase f of x equal to e to the x. And so this is on that previous page where I was talking about we could end up with this whole family of functions. This is an example of that family of functions. And again, this is because no matter what that constant number is, it could be anything from 0.001 up to 17 billion. If I take the derivative, it's going to end up being 0. So that, the constant there, the derivative with respect to that piece is always going to be 0. So again, that's why you end up with a family here. So let's look at another example. So here we have that lower f of x is equal to 4x to the fourth. And again, what we're trying to do here is we're trying to find a function that when we take the derivative of it, we're going to end up with 4 times x to the fourth. And so again, we could start by making a guess. And this is where that idea that I'm going to kind of have to think backwards from what we've done before is going to help me. So I notice here that I've got x to the fourth. And so I know if I were to kind of think of the reverse of the power rule, if I had an x to the fifth, and I were to take the derivative of x to the fifth, I know that I'm going to end up with an x to the fourth. Now the part that I've got to worry about though is what goes here out front. Well, I know that if I have x to the fifth, when I go to take the derivative of x to the fifth, I would end up with 5x to the fourth. But I want 4x to the fourth. So what if we put 4/5 out front here? Notice if I take the derivative of this function, I would end up with 5 times 4/5, which would just give me 4, times x to the fourth, which is exactly what I want. But, just like we saw up above, there are other functions. So, for example, I could define capital F of x equal to 4/5 x to the fifth plus 101. Oops, that's 100, not 101. 101. Notice, if I take the derivative of this, I'm still going to end up with 4x to the fourth, which is what I'm looking for. And again, it's because that derivative with respect to x of 101 is just going to be 0. So any constant number will work there. So just like up above, I could define a family of functions equal to the following. So we're going to learn some rules that are going to help us compute antiderivatives, but the process is typically much more difficult than finding derivatives. And it sometimes takes some ingenuity to come up with the correct answer, and in addition, there are even cases where it's impossible to find an expression for the antiderivative. So the ones that we look at in this section are going to be fairly easy ones, like the ones that you just saw. And so it ends up that mean value theorem that you saw previously can actually help us find antiderivatives. And so previously in the section on the mean value theorem, you already saw this corollary 2. And we're going to add in this new corollary 3. And it ends up that corollary 2 can help lead us to corollary 3. And your book talks more about how to prove that, so I'm going to leave you to read that section on your own. But corollary 3 essentially says, if f of x and g of x are antiderivatives of the continuous function f of x on the interval, then there exists a constant c such that g of x is equal to f of x plus c for all x in I. So in other words, what this is really saying is once you find the antiderivative, any other potential antiderivative that you can find is only going to differ by a constant. And so that's why in these examples, once we get it into this form, since c is any constant, you have defined what we call the general antiderivative. In other words, since all the antiderivatives can only vary by a constant, and that's what corollary 3 is essentially telling us, once you define that family, you've defined what we call the general antiderivative. So let's look at several examples of, again, finding antiderivatives, and we're going to talk through that process of, working backwards. So here we have f of x is equal to 5 times 1 minus x squared. So to make this one easier for me, I am going to go ahead and multiply through by the 5. And my goal here again is I want to find a function whose derivative is equal to 5 minus 5x squared. So I can do this term by term. So looking at the first term, I need a function whose derivative is just 5. Well, the only function that we would get that from is 5 to the x plus some constant, and it can be any constant. And now let's look at the second term. So here I need a function whose derivative is negative 5x squared. Well, similar to the problem that we looked at earlier, I know that the x portion of the function is going to have to be x cubed. Because if I take the derivative of x cubed, I know in the exponent I'm going to end up with x squared. So now I have to kind of think through what constant should I put out front here so I end up with a 5 out front when I take the derivative. Now I know when I go to take the derivative of x cubed, that's going to be equal to 3x squared. But instead of 3x squared, I need it to be 5x squared. And so if I were to put out front here negative 5 divided by 3 plus c, notice if I take the derivative, here I'm going to have x squared, and then I'm going to have minus 5 divided by 3 times 3, which is negative 5. Now remember that c can be any constant, so we can really just combine those two together, and we end up with 5x minus 5/3 x cubed plus c. Because again, c is arbitrary, it's just any constant. And so since the value of c doesn't matter, if I add two constants together, I just end up with another constant. And so I'm intentionally not putting a 2 in front of there, I guess what I'm saying. And again, that's because the c is arbitrary. Now let's check our work. And we're going to check that the derivative of capital F is really equal to lower f. And we need to do that again because that's the definition of an antiderivative. So looking at capital F, if I take the derivative of 5x, I'm going to end up with just 5. If I take the derivative of the minus 5/3 x to the cube, I'm going to end up with minus 5/3 times 3 times x squared by the power rule. And c is again just a constant, so the derivative of that with respect to x is 0. And so notice here I end up with 5 minus 5x squared, which is in fact equal to f of x. So that one checks out. All right, let's look at another example. So here I'm going to find the antiderivative of f of x is equal to the cosine of 3x. Now we know that, minimize that. There we go. We know that if capital F of x is equal to the sine of x, then the derivative of that function is the cosine of x. So that kind of gets us to the right track because we're looking for a function whose derivative is equal to the cosine of 3x. Here we have one whose derivative is the cosine of x. So we can think of what we know about the chain rule with our trigonomic functions. So let's let capital F of x be equal to 1/3 sine of 3x. And now let's check and see what we get. So to check this, again, I'm going to look at the derivative of f prime of x. Now, I will say I'm using a little bit of poor notation because notice I'm defining f of x two different ways. So if we wanted to, just to make that a little bit clearer, since this one was just a demonstration, I could, for example, call these both g. So let's take that derivative of capital F of x. So notice that by the chain rule, we're going to have the following derivative here. Our constant stays out front. We know that the derivative of the sine of 3x is going to be equal to the cosine of 3x. But by the chain rule, I also need to multiply by the derivative of 3x, which is equal to 3. And notice this becomes 3 times 1/3 is 1. So we get the cosine of 3x, which is in fact equal to f of x. And so that checks. Now, I will say your book is not going to require you to do any of the checks. So in other words, once you find the antiderivative, take the derivative of it, make sure you have the original function. But while you're getting used to this idea of the antiderivative, I think it's a really good idea to help you build that intuition to go ahead and always do that check. In other words, take the derivative of the antiderivative and make sure you get back to the original function. So here's another example. And so this one's very similar to the ones that we've seen before. And so again, the idea is we're trying to find a function whose derivative is equal to this function. And we have a polynomial here, and we saw with our other polynomial examples that really what we're trying to think of is we're trying to think of applying the power rule, but we're moving backwards. So I need a function whose derivative is equal to x to the third. Well, I know that if I take the derivative of x to the fourth, I'm going to end up with 1/4 x to the third. But, or probably 4 times x to the third. But I don't want to have a 4 out front, I want to have a 1. So I could have a 1/4 here. And so notice if I took 4 times 1/4, that would give me my 1, and I'd have x to the third. Similarly, I've got 1/3 x to the third, and then minus 5/2 x to the squared. And then again, we're going to put that plus c, where c is a constant, because we know that we're defining the general antiderivative here, and anytime I take the derivative with respect to c, which is a constant, with respect to x, I'm going to get 0. So then again, we could do a check here, where we look at the derivative of capital F of x. And so again, using my power rule, I'm going to have the following. And notice that is equal to our original function, so that does check out and our antiderivative looks good. Here is another example. And so notice this one involves e to the x. So this one's a little bit trickier. When I go to define my capital F of x, again I'm going to look at this term by term. Well, I know that here I've got an e to the negative x squared. So I know that the function that's going to give me the derivative e to the negative x squared is going to have to involve an e to the negative x squared, because the derivative of e to the x is e to the x. But here I'm kind of thinking of a reverse chain rule. And so I know that if I take the derivative of e to the negative x squared, that's going to be equal to e to the negative x squared multiplied by the derivative of what is in the exponent. So in other words, it's going to be multiplied by -1/2. But I don't want a -1/2 out front, I want a +1. So to negate that -1/2, I can multiply by a -2. And then very similar for the next term, I know I'm going to have an e to the -2, but if I were to take, e to the -2x, if I were to take the derivative of this, I would end up with e to the -2x times the derivative of -2x, which is a -2. But I don't want a -2 out front, I want a -1. So I can multiply by 1/2 here to make sure I get that. And then to do a check, I'm going to take again the derivative of the antiderivative to see if I get back to the original function. So applying the chain rule to the first term, I'm going to end up with e to the -x divided by 2, multiplied by my 2 constant that I had, and then by application of the chain rule, I'm going to multiply by -1/2. Similar for the next term, I'm going to have 1/2 times -2 times e to the -2x plus 0, because the derivative of the c is 0. Notice this is going to give me e to the -x divided by 2 minus e to the -2x, which is equal to my original function, so I get back to exactly what I want. Alright, so right here we've got several examples of antiderivatives. Your book works through lots of examples as well. They're different than the ones in the video. So as always, I recommend to go and look through all of those examples. And then you can see from all those examples, you do end up with these general forms for certain common antiderivatives. All right, so let's look at just a couple more examples. So again, we're going to find the general solution. Finding the general solution of a function. So if your textbook asks you to find the general solution, this is the exact same thing as finding the antiderivative of the function. So this is the same thing as finding the antiderivative of the function f of x equals t squared times 1 plus t squared. To make this easier on myself, I'm going to go ahead and multiply that t squared through. And so notice here, now to find the antiderivative, I'm kind of thinking again of that reverse power rule, and I'm going to end up with the following. And since it's asking for the general solution, we typically don't use the antiderivative notation. We instead write that as y is equal to 1/3 t cubed plus 1/5 t to the 5th plus c. And now to do our check. Notice, if we take the derivative of y with respect to x of the function y here, I'm going to have, by the power rule, 3 times 1/3 t squared plus 5 times 1/5 t to the 4th plus 0, which is equal to t squared plus t to the 4th. Now, one of the nice things about using this notation is I think this notation makes it a little bit clearer what it is we've been doing. We identified this y. Then, as our check, we took the derivative of that y. And we found that that derivative was equal to this. Well, notice if we go right back up to the top, that is exactly what we have here. So again, the idea with the antiderivative is that you're given the derivative and you're asked to find the function that has that derivative. And when we say the general solution, that's when we're including this c, because we know that there's a whole family of functions that once we take the derivative of it, we're going to get back to that function that we're given. All right, one more example here. So at the very beginning of this video, I said we will look at examples where we find a family of functions, but we're also going to look at what we call initial value problems. Well, it ends up initial value problems are very similar to finding the general antiderivative. We just have one more step, and let's see what that looks like. So here we have that dy dx is equal to x squared divided by 3. Notice that is the same thing as 1/3 x squared. So first, we're going to find the general antiderivative. So again, thinking of kind of a reverse power rule here, we're going to have 1/9 is equal to 1/9 x cubed plus c. So therefore, y is equal to 1/9 x cubed plus c. Now, we always want to go ahead and, especially at this stage where we're trying to gain that intuition, let's go ahead and just double check that y to make sure that function looks good. So notice if I take the derivative of y with respect to x, that's going to be equal to 1/9 times 3 times x squared plus 0, and again, that's by the power rule. So I end up with 3/9, which is the same thing as 1/3 x squared, which is exactly what we have up top, so our check looks good. So next comes the initial value part. So notice what we're asked to find is the solution that has y0 equals to 2. So right now our solution has this c in it. For the initial value problems, we're essentially finding what value of c we have. And so next, we need y at 0 to be equal to 2. So all we're going to do is start with this highlighted piece here. So we know if we substitute in x for 0, we should end up with 2. So in other words, 2 is equal to 1/9 times 0 squared plus c. And if we solve this, we find that c is equal to 2. And our initial value problem, the solution for it, is that y is equal to 1/9 x cubed, but now instead of plus c, we're going to have plus 2. And so again, the general solutions will have the c. The initial value problems are where we're actually finding the value or a specific value for c. And so for the initial value problems, you're just going to do one more step. So as always, if you have any questions over this, please let me know.